To follow up on the idea of photoelectron spectroscopy, here's some actual data from two molecules, from hydrogen and nitrogen, showing their photoelectron spectra. And basically what we're doing here is we have our, say, our nitrogen molecules. We're sending in light, and this is UV light. You can see this from the, from the energies here, in the tens of electron volts. And this is sufficient energy to actually remove an electron and ionize our molecule. And then what we do is we measure that electron and how many electrons do we get out, and that's sort of what we have plotted here. As we increase the energy, that's going to get electrons that are more tightly bound to the molecule to be removed. So if we look at hydrogen here, we can see, right, our molecular orbital diagram is that we have two electrons in a bonding orbital, a sigma G orbital. And when we do the photoelectron spectrum experiment, we see there's a set, and we'll go over why there's a set of these. It has to do with vibrations. Well, we won't go over it, but just to mention that, right? Rather than this being one peak, we have a set of peaks. But this set of peaks here corresponds to those bonding electrons. And we only see one set of peaks. There's not a separate set of peaks because we only have one orbital, molecular orbital that's occupied. And the reason we get all these separate peaks are due to vibrations of the molecule. We can model that with a harmonic oscillator. When we look at nitrogen, we can see, of course, the bonding in nitrogen has more orbitals occupied, right? We have these occupied pi u orbitals, right? Our pi bonding orbitals, as well as our sigma bonding orbital that's formed from the pz orbitals, as well as our two s orbitals, right? We have our bonding and anti-bonding down here. And so when we do this experiment for nitrogen, what we see is that at lower energies, so the lower the energy, ionization energy, the higher energy orbitals, these electrons will be ejected first. And so the first peak we see is from the pz bonding orbitals, right? This 3 sigma G orbital, 3 just meaning it's the third sigma orbital. Then we see a set of peaks from the pi bonding orbitals. And then we actually even see the anti-bonding orbital show up here. It would have to go quite a bit higher in energy to see these sigma bonding orbitals from the 2s electrons, right? So, but we have experimental evidence in it. We can interpret these to show that these are these particular orbitals that are present, right? We can actually tell sigma and pi orbitals apart from each other by properties of the electrons that come off. And so this gives us evidence that we do really have these molecular orbitals that are present, and that this isn't just some theoretical exercise. This is also, we can measure that this is actually happening within the molecules we're looking at. For the final video of our of this chapter, we'll be looking at visualizing these molecular orbitals using computational chemistry. We'll cover computational chemistry in a couple of chapters, but we can use the tool of computational chemistry to actually predict probability distributions and the wave functions that belong to these orbitals. So instead of these sort of drawings that I have, we can see, at least according to our best approximation methods using variational theory and perturbation theory, we can get at what these orbitals actually look like and what their shapes look like.